In this first AC/DC SMPS Basics course, we will address the following topics. Why would we want to use rather complex switch mode power topologies for converting mains input to a regulated voltage or current output? Why can't we just use traditional techniques? What switch mode power conversion topologies are available? We will show the most common and popular ones. We will conclude this short course with an overview of the components that NXP produces to implement the aforementioned switch mode topologies, but we will discuss the details in the second basic AC/DC SMPS course. What is the benefit of switch mode power conversion? Let's assume that we have 230 volts AC available from a normal European wall outlet, and that we need to create a power supply that delivers 12 volts DC to a certain load. The 12 volts can be created by using a linear regulator circuit, but the disadvantage is that a linear regulator has a very low efficiency, certainly when the input voltage is high and the output voltage is low. Moreover, when a linear regulator needs to deliver substantial power, the construction will be relatively large because of the high amount of power that must be dissipated. Though the concept of linear regulation is simple, it may not be a very feasible solution for most AC to DC conversion purposes. The 12 volts can also be made by using a 50 Hz or 60 Hz iron core transformer. That is generally already a lot more efficient than linear power regulation. Nevertheless, the low AC frequency, 50 or 60 Hz, requires a rather large iron transformer core and a lot of copper wire, which makes the construction bulky and heavy. A switch mode power supply overcomes the two disadvantages. It can be both efficient and small. A switch mode power conversion network consists of switches and energy containers. The switches are usually MOSFETs or bipolar junction transistors and diodes. The energy containers are inductors and capacitors. By switching the switches with the right duty ratio and frequency, power is transferred from the source to the load, while the correct output voltage, 12 volts in our case, is maintained. The required amount of power can be transferred either by transferring large chunks of energy at a low frequency or by transferring small chunks of energy at a high frequency. The advantage of switching at a high frequency is that the energy containers, the inductors and capacitors, can be small and therefore light and cheap. The disadvantage is that more switching actions per unit time are required, and unfortunately more switching actions lead to higher switching losses, mainly in the semiconductor switches. To convert power from the AC mains voltage to some regulated DC output voltage, first the AC voltage is rectified using a full-wave or half-wave rectifier circuit. Now the voltage on the buffer capacitor is a DC voltage. The actual power conversion step is being performed by the two switches and the two energy containers, one an inductive and one a capacitive element. As an example, a flyback topology is shown. In order to regulate the output voltage, the output is monitored and information is fed back to the controller. Based upon the received information, the controller drives switch 1 and implicitly switch 2 in a way that the required output voltage is obtained. Depending on the application, one may want to use either an unisolated or an isolated switch mode converter to provide the power for the specific purpose. Unisolated SMPS circuits do not implement a galvanic isolation between the AC mains and the output voltage or current. For that reason, the output of an unisolated SMPS is not touch-safe. And the same is true for the application that receives its power from the unisolated SMPS. Isolated SMPS circuits do implement the galvanic isolation. Therefore, the output of such a converter is touch-safe, and so is the application that is hooked up to the isolated SMPS. Let's have a look at the three elementary unisolated switch mode topologies. The first one is the so-called buck or step-down converter. As the name already suggests, this converter can be used in circumstances where the required output voltage is lower than the input voltage. The converter converts the voltage downwards. The basic operation is as follows. When the switch is closed, current starts to flow through the components as indicated by the red arrow. If we assume that the output voltage of the buck converter, VO, is constant, there is a constant voltage drop across the inductor. As we know from elementary network theory, a constant voltage drop across an inductor causes the current flowing through that inductor to rise linearly with time. dL dt is constant. And the proportionality factor is the inverse of the inductance value L of the component. On the right-hand side, the linear increase of the current in the inductor is shown in a graph. This operation phase of a converter, where the first or primary switch is closed, is called the primary stroke. When the switch is turned off, the current in the inductor keeps flowing, but the only path that the current can take is through the diode, which basically operates as the second switch in the power conversion network. Again, there is a constant voltage across the inductor. Please note that the sign of the voltage across the inductor was changed when the switch turned off and the diode turned on. Because of the new voltage across the inductor, the current decreases linearly with time. This is shown in the waveform graph on the right-hand side. In the graph, the rising and falling slope are shown as approximately the same, but with a different sign. In practical circumstances, this is generally not the case, but for the sake of clarity, they are shown as such in this explanatory graph. The operation phase where the second or secondary switch is closed is called the secondary stroke. The relation between the input voltage Vi and the output voltage Vo is given in the first equation. The output voltage is equal to the duty ratio, delta, times the input voltage. As delta is always a value between 0 and 1, the output voltage will always be lower than the input voltage. And that is why this converter topology is called a step-down or buck converter. The voltage rating of the semiconductor switches is given in the two subsequent equations. As you can see, the voltage rating of both the switch, which in general will be a MOSFET, and the diode should at least be equal to the input voltage plus a bit of margin. The second converter topology is the step-up or boost converter. This converter can be used in circumstances where the required output voltage is higher than the input voltage. The converter converts the voltage upwards. The basic operation is as follows. During the primary stroke, that is when the primary switch is closed, current starts to flow through the components indicated by the red arrow. Assuming that the switch is ideal, the voltage drop across the inductor is equal to the input voltage. The constant voltage drop across an inductor causes the current flowing through that inductor to rise linearly with time. dL dt is constant. And the proportionality factor is 1 over L. The linear current increase is shown in the graph next to the circuit diagram. In the secondary stroke, the current in the inductor keeps flowing, but the only path that the current can take is through the diode and subsequently into the capacitor. Again, there is a constant voltage across the inductor, namely VO minus VI. Please note that the sign of the voltage across the inductor was changed when the primary switch turned off and the diode or secondary switch turned on. Now the current decreases linearly with time. This is shown in the waveform graph on the right-hand side. Again, the relation between the input voltage Vi and the output voltage Vo is given in the first equation. The output voltage is equal to the input voltage divided by 1 minus the duty ratio, delta. As delta is always a value between 0 and 1, 1 minus delta is also a value between 0 and 1. And that results in the output voltage being always higher than the input voltage. The voltage rating of the semiconductor switches is given in the two subsequent equations. As you can see, the voltage rating of both the switch, which in general will be a MOSFET, and the diode should at least be equal to the output voltage plus a bit of margin. The third and last converter topology is the step-up-down or buck-boost converter. This converter can be used to either realize an output voltage which is lower than the input voltage or an output voltage which is higher than the input voltage. One side effect of this converter is that the sign of the output voltage is changed. The basic operation is as follows. During the primary stroke, current flows through the components indicated by the red arrow. The voltage drop across the inductor is equal to the input voltage. The constant voltage drop across an inductor causes the current flowing through that inductor to rise linearly with time. dL dt is constant. And the proportionality factor is 1 over L. The linear current increase is shown in the graph next to the circuit diagram. In the secondary stroke, the current in the inductor keeps flowing, but it can only take the path indicated by the red arrow. Through the diode, the current charges the capacitor. Also during the secondary stroke, the voltage across the inductor is constant, namely minus VO, which causes the current to decrease linearly with time. This is shown in the waveform graph on the right-hand side. The relation between the input voltage Vi and the output voltage Vo is given in the first equation. The output voltage is equal to minus delta times the input voltage divided by 1 minus delta. When delta is exactly 1/2, the output voltage is equal to the input voltage, apart from a sign change. When delta is below 1/2, the output voltage is lower than the input voltage. And when delta is above 1/2, the output voltage is higher than the input voltage. The voltage rating of the semiconductor switches is given in the two subsequent equations. As you can see, the voltage rating of both the switches should at least be equal to the maximum voltage difference that exists in the circuit plus a bit of margin. After the three basic unisolated switch mode topologies, we'll have a look at the most popular isolated topology, the flyback converter. We will study the discontinuous mode of operation. Discontinuous in this sense means that during one complete cycle of operation, first energy is stored in the magnetic element, during the primary stroke that is, and subsequently, all the stored energy is released from the magnetic element during the secondary stroke. Only after that, a new operation cycle is allowed to start. We'll have a look at the operation principle. When the primary switch is closed, the input voltage appears across the primary inductance of the so-called flyback transformer. This voltage causes the current in the primary inductance to rise in a similar way as we have seen on the previous slide. The current rise during the primary stroke is shown in the topmost graph. By the end of the on-time period, the current in the primary inductance has risen to a value ILP, which is equal to the input voltage times the on-time divided by the primary inductance value. Because the secondary switch is open, there is no current flow on the secondary side of the circuit, as can be seen in the middle graph. The third graph shows another important parameter, the voltage across the primary switch. Of course, the voltage across this switch, mostly a MOSFET, is 0 volts during the primary stroke because the switch is closed. The secondary stroke starts by opening the primary switch and closing the secondary switch. The current that was flowing in the primary inductor of the flyback transformer cannot continue to flow because the circuit is interrupted now. This fall of the current to 0 is reflected in the upper graph. But because the primary and secondary inductance form a set of coupled inductors, the magnetic energy that is stored in the flyback transformer can be released via the secondary inductor. The starting value of the secondary current, denoted as ILS, is equal to ILP multiplied by the winding ratio of the transformer, where the winding ratio is equal to the number of turns of the primary inductor divided by the number of turns of the secondary inductor. With a fixed voltage across the secondary inductor, namely the output voltage, the current on the secondary side decreases linearly with time. This is shown in the middle graph. The lower graph shows the voltage across the primary switch. During the secondary stroke, that voltage is equal to the input voltage plus the winding ratio times the output voltage, or usually for short, VI plus NV out. In discontinuous operation mode, the secondary stroke ends when the current in the secondary inductor has fallen back to 0. In the subsequent phase of operation, both the primary and the secondary switch are open. There is no energy storing or energy release during this phase. The time during which nothing is happening is usually called dead time. During dead time, there is no current flow in the primary and secondary winding, as can be seen in the upper and middle graph. The lower graph shows that the voltage across the primary inductor falls to VI. A special case is the case where dead time is zero. This mode of operation is usually called critical or boundary conduction mode. It is a more efficient mode because the switches and the storage elements are continuously being used and not left in an idle state during T dead seconds. The voltage waveform as shown in the lower graph is an idealized waveform. The actual waveform would only be such if the operation of the transformer, or better, set of coupled inductors, would be ideal. And in a practical situation with a real transformer, that is not possible, of course. With a real transformer, we will see some voltage ringing when the secondary stroke begins and after the secondary stroke ends. The damped voltage oscillation, or ringing as we usually call it, at the beginning of the secondary stroke is caused by the leakage inductance of the transformer. The ringing will cause the maximum voltage across the primary switch to rise above VI plus NV out. The higher the leakage inductance, the higher the peak voltage, shown as V peak in the graph, will be. When selecting a primary switch, the voltage rating must be such that it can easily withstand this V peak voltage. After the secondary stroke, there is another ringing waveform which is caused by the primary inductance, LP, and the capacitance of the primary switch, CDS. This ringing leads to a sequence of peaks and valleys during the dead time. In a smart switching strategy, the occurrence of valleys can be used to reduce power loss and switching noise. We will go into the details in the next course module. So far, we have seen how power is transferred from input side to the output side through a switching network. However, the switching alone does not result in transferring exactly the desired amount of power to the output. For that purpose, we need some kind of output regulation strategy. Taking the flyback converter as an example, we can transfer packets of energy at a fixed frequency and vary the size of the energy packets. This is done by keeping the switching interval T constant and vary the on time of the primary switch T on. A second method would be to keep the energy packet size constant and to transfer more or less energy packets per unit time in order to realize the desired output power. In this case, T on is fixed and T is variable. The third method is to vary both T and T on using a smart strategy. In this way, a so-called quasi-resonant mode of operation is achieved. More details about quasi-resonant mode will be given in the subsequent course module. It is the task of the SMPS controller IC to drive the switches in the switching network in such a way that the output is regulated in the desired way. Simple controllers will usually have just operating strategy implemented, and more advanced controllers will change the control strategy dynamically. In order to regulate the output properly, an SMPS controller will need information about the output. Again, we will take the isolated flyback converter as an example. When the ultimate goal is to regulate the output voltage of a power supply, out1 in this example, the most straightforward thing to do is to measure the output voltage, out1, directly by using a regulator circuit and transfer the information across the isolation barrier to the SMPS controller. Crossing the isolation barrier is usually done with an octocoupler. Because we sense the output property on the secondary side of the switching network, this feedback method is called secondary sensing. For its own operation, the SMPS controller IC receives its power, VCC in the diagram, via an auxiliary winding on the transformer. The main advantage of this method is that you are measuring exactly the property, out1, that you want to regulate. And in that way, one will generally be able to achieve the best regulation results. Disadvantages are in the costs. Octocouplers are relatively expensive, and in the required additional circuitry that consumes more energy. An alternative to secondary sensing is primary sensing. In the primary sensing case, the voltage that the auxiliary winding produces for the operation of the controller IC is also used to regulate the output voltage out1. The idea behind this principle is that the VCC voltage that is generated by the auxiliary winding is proportional to the voltage that is generated by the transformer's secondary winding that produces out1. Appropriate regulation of VCC will therefore result in appropriate regulation of out1. The main advantage is obvious: cost saving, and the regulation circuit can be dimensioned in a way that power consumption is minimal. However, there is also a serious disadvantage. Only in transformers that have a perfect coupling between the secondary winding and the auxiliary winding will produce an accurately regulated output voltage. Unfortunately, these transformers do not exist, and constructing a transformer with at least very good coupling between the two windings will result in a complex construction that is relatively expensive. Therefore, reduced regulation accuracy must be accepted when primary sensing feedback is used in an SMPS topology. In practical circumstances, primary sensing can be a good choice for low-power switch-mode power supplies, but for most high-power circuits, secondary sensing will be the preferred method of feedback. A completely different type of SMPS is the resonant converter. In this example, we show the frequently used so-called LLC resonant converter topology. The first L is the magnetization inductance of the transformer, LM. The second L is the series or resonant inductance, LR. And C is the capacitance in series with these two inductances. The resonant converter topology is more complex than the buck, boost, and flyback converter topologies. In the power conversion network diagram, we see 4 switches, 2 MOSFETs and 2 diodes in this case, and 2 inductive components, a transformer and series resonant inductor, and 2 capacitive components, the resonant capacitor C and the output capacitor. Unlike the transformer in a flyback topology, the transformer in a resonant topology actually operates as a transformer. When energy is injected on the primary side of the transformer, it is directly transferred to and consumed on the secondary side. Let's take a simplified look at the elementary operation of the resonant converter. The voltage waveform at the half-bridge node that is produced by the resonant converter and the 2 primary switches is a symmetrical square waveform. 50% of the time the voltage value is Vin, and 50% it's 0 volts. To take away some complexity, let's replace the left-hand part of the circuitry. The controller and the half-bridge circuit are now replaced by a symmetrical square-wave voltage source. When a resistive load is connected to the output, the secondary windings, in combination with the secondary switches, diodes in this case, form approximately a resistive load on the secondary side. If, therefore, we assume that the transformer is ideal and no magnetic energy is stored inside the transformer, we can make a significant simplification of the load side of the circuit. It's a simple RLC network that remains. If we would not neglect the magnetic energy storage in the transformer, there would be an inductor Lm representing the magnetization inductance of the transformer in parallel with the resistor. But in this elementary explanation of the operating principle of a resonant converter, it's appropriate to eliminate Lm from our analysis. The qualitative behavior of the RLC circuit is described in nearly all textbooks on network theory, but we'll give a quick summary. We're having a look at the power transfer function of the RLC circuit. The resonant frequency, Fres, of this circuit is determined by the value of the inductor and the capacitor. At the resonant frequency, the impedance of the series resonant LC circuit is 0. This is the condition for transferring the maximum amount of power. In the graph, this is the peak of the curve where the gain, A, is 0 decibel. Both on the left and right side of the peak, the gain is below 0 decibel. If we are not in a position to vary the amplitude of the square waveform signal, there's only one method left to control the amount of power that is transferred from the input to the output. By varying the frequency. Below the resonant frequency, the behavior of the LC series circuit is predominantly capacitive. You could consider the inductor as a short. So reducing the switching frequency leads to a reduction of power transfer. Above the resonant frequency, the behavior is predominantly inductive. You could consider the capacitor as a short. And that results in a reduction of output power when the operating frequency increases. Normally, an LLC resonant topology uses only the inductive side of the transfer function, the part right of the resonant peak, to control power transfer from input to output. Of course, this is a somewhat oversimplified approach of the operation of a resonant converter. But the basic idea is exactly as outlined in this short explanation. In the subsequent course module, more details of resonant converters will be presented. In order to generate exactly the right amount of power on the output that is desired, the output must be monitored, and that information must be presented to the resonant controller via a feedback loop. This control and feedback loop is not essentially different from a loop that is used together with a flyback converter. In this first AC/DC Basics course, we've seen isolated and unisolated SMPS solutions. Many of the NXP SMPS ICs can be used for controlling both buck or buck boost and flyback topologies. Some NXP products that can be used for the implementation of a buck or a buck boost converter are the TEA152X family of ICs. These ICs have an integrated MOSFET power switch, the primary switch, and are intended to be used in the lower power segment. The TEA172X family of ICs. These ICs do also have an integrated MOSFET power switch and are also intended to be used for low power segment. The most remarkable difference with the TEA152X family is the extremely low idle power that is consumed by a TEA172X application when the power supply is in standby mode. TEA150X, TEA153X, and TEA155X family members need an external MOSFET power switch, but they can be used for much higher output power. A special device is the UBA3070 Boundary Conduction Buck Mode LED driver controller. This IC also needs an external primary switch, and its sophisticated operation allows the creation of very efficient LED driver applications. The other unisolated converter that we presented was the boost converter. Boost converters are less often used in power supply applications as a standalone circuit, but NXP ICs that can be used for controlling a boost converter are the same ICs as the controllers for buck and buck boost. Next to that, a dedicated boost converter IC for driving LED strings is available, UBA3077. One of the most important features of the boost converter topology is that it can easily be used as a power factor correction controller. Details of the power factor corrector are presented in a subsequent course module, but to give a preview of some of the devices that include a PFC stage, we mention the standalone PFC family of ICs, TEA174X, the TEA175X family, and the TEA1713 IC. For isolated SMPS solutions, we have seen two main topologies. Let's have a look at the IC implementations that NXP has for flyback SMPS solutions. TEA152X for low output power, TEA172X for low output power in combination with low standby power, TEA173X for medium output power. This controller IC requires an external primary switch, and the TEA150X, TEA153X, and TEA155X family of ICs for higher output power. All these ICs also need an external primary switch. Finally, there is also a family of flyback controllers that has an integrated PFC stage, the TEA175X series. And finally, we have dealt with resonant converters. The NXP implementation for LLC resonant converter controllers is the TEA161X family. A special LLC resonant converter IC is TEA1713, which has a boost mode PFC controller stage built in. This concludes the first AC/DC SMPS Basics course module. Thank you for your attention.